So thank you for hosting me. Thank you for having me here. And welcome again to YAS 2020. As the talk title suggests, that Call of Duty Modern Browser Warfare. So we will be discussing about certain techniques which I have figured out during my research done towards browser security and exploiting the core policies implemented by the different vendors. So without further delay, let's get started. Okay, so before we get started, this is something about myself. My name is Dhiraj Mishra. I work as a senior security consultant for company called Congnosec, and I tweet at random Dhiraj and blog at input0.io. So if you have any queries regarding this specific topic or any other topic such as fuzzing, so you can do not hesitate to reach me out on any of these. So before we get started, I just wanted to give you an idea about how in general a browser works, because that's very important. So I'll be taking you to each and every sectors and block which you see over here at a very high level approach, basically. So we'll start with the user interface. I'll take you to each one of them and what's the actual role about all these blocks are when we talk about browsers. So if we talk about user interface over here, so user interface is something which whenever you open a browser, you see your back button, your forward button, the settings tab, the home button, everything which is being accessible from the user level to in a browser, the user interface block is responsible to do so. The second one is browser engine. Is basically facilitates the data between the rendering engine and the UI, the user interface. The third block is rendering engine. Now, rendering engine actually does a lot of work as part of the core browser functionality. So whenever you visit any website or anything in a browser, so it picks all the JavaScript, the CSS, the Bootstrap, the HTML, everything for you, and render it for you on the browser. So that specific job has been done by the rendering engine part. Now, rendering engine has three different main core components divided further. The very first one is networking block, then you have JavaScript interpreter, then you have UI backend. So when I talk about the networking block, so any protocol handling stuff in browser is being done by the networking block. So like if you visit HTTP, HTTPS, or FTP, so all those protocol handling things has been done or managed by the networking block. Apart from that, networking block is also responsible for resolving your DNS queries. The second block is JavaScript interpreter. What happened over here is, like, if in case you're writing certain set of code, and let's suppose a scenario where apparently you forget to close division tag or any other tag in HTML or CSS or somewhere, but still browser handles those small certain exceptions and will try to display the data for you. So that exception handling stuff is being done or handled by the JavaScript interpreter. Then you have UI backend. So UI backend is responsible for designing and collecting all the data so that it can push back to the user interface at the user level, then it is being showcased to the user. At the right-hand side, you have a data persistent block. Now, whenever you visit a website, you enter your username and password. So browser gives a pop-up on the left top corner stating that remember me. So whenever we do that, that specific chunk of data has been stored in the data persistent block. So this is a very high level approach of how in general browser communicates and what all blocks or what all sectors are responsible to make browser works. Moving forward, this is just to give more information about the rendering engine part. So Chrome uses Blink, Internet Explorer has Trident, Firefox uses Gecko, and Safari has WebKit. So these all are types of rendering engine being used by like most of the common or the standard browsers. And if we talk specifically about the JavaScript engine, so Chrome uses V8, Internet Explorer and Edge uses Chakra core. Firefox have their own SpiderMonkey. Safari uses again WebKit, which is also known as JavaScript core. Recently I came across with Herms used by Facebook in their native applications. So these all are types of JavaScript engine basically which is being used by most of the common browsers or the standard browsers out there. So moving forward, let me give you an idea about what origin is, because we will be going to talk about what same origin policy is and how do we bypass them. So origin basically is a combination of schema, hostname, and port. So schema can be your any protocol, which is HTTP, HTTPS, FTP, and so on and so forth, where www.input0.io would be your host name, and 8080 port is your standard port. So combination of this entire three makes an origin. So what is same origin policy? So let's suppose a scenario where you open your browser, you navigate to facebook.com, and at a certain moment or time, you open a new tab, browsing evil.com. Now you trust your browser that there is no data sharing between the different origins. So when I say facebook.com and the other tab has evil.com, they both are different origins. You trust your browser that there is no data sharing between both of them. So this happens because if the same origin policy has been implemented correctly. But let's suppose that you have, let's suppose a scenario where the browser doesn't implement the same origin policy properly. So, and the evil.com can make an XML HTTP request to facebook.com and get a chunk of data or session ID and etc. So in that case, we are actually evading the same origin policy. So this is a very, again, high-level overview what SOPs are and how and why it is important as the core functionality of the browser. Okay, so moving on, same origin policy was actually implemented back in 1995 in Netscape Navigator, now owned by Mozilla. So the fun fact over here was the initial release for Netscape Navigator was on 15th of December 1994. And it took them an year to understand the actual importance of same origin policy. So this is just a small idea about when the SOPs were implemented. Moving on, let's have a look on same origin policy bypass and how do we evade using different techniques. So during my analysis for different browsers and finding same origin policy, I figured out two SOP bypass for most of the common browsers. Over here at the left-hand side, it's Samsung Internet Browser, and the second one is a privacy-based browser. The CV was assigned for both of them, so let's jump in directly to the code, how I figured this out. So I was playing around with tons of functions on JavaScript around there, like for example, window.open with document.body.inner.html and so on and so forth. So I created a function Go with onClick, and what this function does is basically it's open a window.open. It tries to open something on your address bar, and over here, if you see, it tries to open www.google.com/CSI. But once when it opens this specific URL, it tries to push the content which is being set by me using body.inner.html. So here it says that please log in with the prompt, email, and password. So whenever you punch in the email and password, that data would be carried back to the attacker's origin. So let me give you a quick overview how this works. So window.open is responsible for opening the URLs which I forcefully try to browse in. And using document.body.inner.html, you can render the content of the page, whatsoever you like to do. Using x.prompt, like it gives you a prompt of please enter your email address and password. So rather than using for x.prompt, you can have a normal form basically to make it more realistic. You can also have a post method while it carries the data and so on and so forth. So just to give you an idea, I have simply used x.prompt. So once when I observed this and it was being passed by Samsung officially, and I went ahead and ported this to an MSF module. So if you go to auxiliary gather Samsung underscore browser underscore SOP underscore bypass.rb in your MSF terminal, so you will find this. It is being pushed by the Rapid7 team when I successfully ported this to an MSF module. So I'll quickly give you a glimpse of how the portability works. So we will be talking about custom underscore JS in coming further slide. But if you see JS equal to where I actually passed the same XML HTTP request and using document.body inner HTML, I said 4 of 4 error and oops, something went wrong and I have to click that. Click a link. So once the link has been clicked, it pops up for the email and password. And when you punch in back, it is being traveled back to the MSF terminal. So I'll showcase you the video POC for this. But yeah, hold on. Apart from that, on the right-hand side block, if you see where x is equal to window.open, data stored target underscore URL. So whatsoever origin you want to spoof, you can set it as like set target underscore URL to HTTPS google.com, or it may be GitHub or Microsoft or any further thing. We also added the store underscore cred functionality in the MSF framework. Now what this does basically is like once the username and password has been captured, it takes that username and password back to the MSF database. So it has been stored that. So store underscore cred is the actual MSF library which is responsible to do so. So in this case, whatever session ID or the username password or anything which is being captured by this module will be traveled back to the MSF database, and it will be stored over there for your future purpose. So it was also being featured on some of the magazines, and yeah. So I went ahead, I performed the same test case on another browser called DuckDuckGo. And in the similar fashion, I was able to bypass the SOP for DuckDuckGo. So this is how the module worked. Let me quickly jump into the video proof of concept. Oh, okay. So when you open your MSF console, you just search for SOP underscore bypass, and you will get the list of modules which are available on the Metasploit framework. Over here, auxiliary gather / Samsung underscore browser underscore SOP underscore bypass is the module which is responsible to do so. On the right hand side, I'm using Genymotion with the vulnerable version of DuckDuckGo. So you do options, and you do set SRV host, which can be an attacker IP in a simple case. And then you have set target underscore URL. You can add whatever origin you want to add. In this case, I'm using https www.google.com/CSI. And once you do that, you can set the URI part to the root domain, and that's it. Your MSF module has been completed, and you can simply run the server and make sure the attacker, you send this crafted HTTP request or this URL to the end victim. And when the victim visit, as you can see on the right hand side on the vulnerable version of DuckDuckGo, it gives a message stating that the page has been moved. Please click here to redirect your browser. So once you click that, it navigates, as you can see, it navigates to google.com/CSI, and using body.innerHTML function, it renders the JavaScript, the malicious JavaScript over here. So here you can put anything like admin@itb.com, and the password can be anything. And once when you do that, it has been pushed back to the MSF framework. Like you can see, collected credential for https www.google.com/CSI with username this and the password this. So this was a very quick portability which happened of my SOP bypass module, and the vulnerable browsers were the Samsung Internet browser and the DuckDuckGo. So moving on, what what would have been more wrong rather than just capturing the username and password? So if you recall the custom_js function on the MSF module, so let's suppose if you don't want to just simply capture the user credentials, you can use your own custom_js to capture any other data. Like you can hook the browser and you can send the malicious pop-up, which actually looks like a system pop-up, and then you can capture all other juicy information. So that's a very common idea about what custom_js does, and it was being also enabled in my module for MSF. Okay, so moving on, let's have a quick look on the code execution vulnerability, which I found out during the analysis of the Firefox browser. So it was a duplicate bug because the Firefox internal team were actually aware of this and they were maintaining a track to mitigate this. So how did I figure out this vulnerability was, I was reading out to the developer guide of Firefox, Chromium, and any other open source browsers. So when I was reading about the under developer.mozilla.org, there's a component called NSI local file. Now, this NSI local file is a component that helps you to navigate to the different path in different platforms and query the state of any file or directory. So basically, you navigate to you can point this component to any directory or to any binaries to have a look on what the state is all about. And this component can be referred by using a string called @mozilla.org/file/local:1. This also creates an instance, which is also known as contract ID. So when I was reading to this document, so I thought about let's have a look where I use this contract ID and the component NSI local file to see whether I can point out or call the system binary file in context of Firefox. So what I did was, when you go to the new tab, opened up a new console, under the console section, I used f_component.class and I created a contract ID, an instance, and I used NSI local file to navigate to see Windows system32cmd.exe, and I said that f.launch. So in particular, over here, the console for the console for Firefox actually allows you to execute arbitrary JavaScript in context of browser. So if you quickly have a look on the POC, so this was the vulnerable version of Firefox running at that specific time. So I opened up Firefox. So it was on version 54.x. I think it was there till 55.x. Now, obviously, this has been patched. So you open up a new tab, you open a console, and once the console has been opened, you push the one-liner command by creating an instance ID and a component using NSI local file. Now, this pops up the cmd.exe. Now, technically, Firefox or the browsers should not allow calling the system binary files using the NSI local file. So the execution of JavaScript is still being there in console for the Firefox, but they have stopped traversing the or pinpointing the state of any binaries using NSI local file. So again, this was a duplicate bug over here. How this can be used, this is not a pro tip, but if in case you are having a sandbox environment in any of your pen test activity or any technology such as Citrix or something, and if they have a vulnerable version of Firefox, which is 55.x or something, so you can use this technique to escape the sandbox environment. So because I found this in one of my engagement and it was working perfectly. So this is just to give you an idea about how the JavaScript executes in context of Firefox. Now, technically, I couldn't figure out it to trigger remotely because it requires that the end user should only run this in a console. So it's a local attack vector where you need the desktop on where you can punch in all those things, and then the CMD has been popped up. Okay, perfect. Moving on, I would also like to share one of my test case for integer under overflow in Firefox, specifically in NSS library. So this was identified as part of my fuzzing, like you can say on my fuzzing time or moving forward. What happened over here is, let me give you an idea what integer under overflow is. So if an integer value used over here or in any function is been less than signed or unsigned integer, then it causes an underflow, which will also trigger a segmentation fault. So what happened is, I'll just quickly take you to the what my fuzzing setup was. So I had a Firefox, and every 5 seconds it used to visit a engine server hosted locally, which simply has index.html page with a simple hello world. Now, I purposely went ahead and used bad SSL over here. Now, I got a sample corpus. Now, corpus is like a sample input, SSL, bad SSL certificate. And using Redumsa, I mutated it like for 100 or 200 times. And I created that bunch of folder. So the engine server was using that bad SSL in every 3 to 4 iterations. And Firefox used to visit it, just add the exception by its own, and then tries to render what was inside the index.html file. Now, at a certain level, when I started doing fuzzing for this specific activity again and again, I triggered a crash at a certain level. And the crash was, when I submitted this crash to the Firefox security team, we went ahead and analyzed that somehow my cert8.db file has been corrupted. Now, cert8.db file is a security certificate file which has been stored separately from your OS. This is under your program files somewhere in Mozilla folder. They don't have your secret keys such as key3.db, but they will definitely have what you have imported, such as certificate authorities or client certificates and so on and so forth. But again, it won't have any private keys. So somehow it looks like my cert8.db file was corrupted, and whenever I used to add exception for the bad SSL, my Firefox used to get crash. So we at least got the hold of what was being corrupted. Thanks to the Firefox team over here who helped me to debug and analysis it further. So the legacy certificate database implementation in Firefox has been written very, very long time back. And there are certain places and functions there where they don't properly sanitize or validate the inputs, which has been coming from the user or from the application or anywhere else. So what happened over here was, when the fuzzing process was happening, there was a SSL metadata key length, which was being greater than as compared to the key length which is being mentioned over here. So there is no check happening on the key length of the SSL certificate during adding the exception. In one of my test case, the metadata for the key length was greater than the actual implementation of the database or the NSS library. So because of that, it causes an integer under overflow, and a segmentation fault was being triggered. So this was being reported by their Firefox bounty program. A patch was pushed. So what patch does basically is, there is a function called ugly_split. Now this does basically a garbage collection. And what happened is, whenever the metadata key length is greater than the actual value or the key length being defined in h_page.c, it subtract the remaining value and then it tries to render the application. So they basically did a garbage collection over here, and that's how they mitigated this specific issue. I personally feel somewhere that fuzzing NSS library again would have a lot of vulnerability out there. There might be an out of bound or any sort of overflow, because looking at the certain code level itself, you will figure out that there is no input validation or the sanitization of what data or chunk has been passed. So it would be a great idea, again, start fuzzing with the Firefox NSS library. So moving on, there's also Firefox caching vulnerability, which I figured out during one of the uh, my bug hunting program with few of my colleagues, Sebastian and Robin. So what happened is, this is very interesting vulnerability so far which I have observed, but technically it cannot be remotely exploited, what I have seen so far. So there was a caching problem in Firefox itself. So you log into your Gmail account from Mozilla, perform any dynamic activity, like you browse your emails, you send, you receive, you check your spams, and so on and so forth. Log out from the mail.google.com or anything, any other application or services which you are using, but do not close the browser. So once you do that, you just simply go to view-source to the post URL, like post login URL, and you will be still able to find that most of the data which you have been dynamically performing onto the application would be visible on the source code. So let me give you an idea by showcasing the proof of concept. So this is the again the vulnerable version of Firefox. They took an year to patch this because again this cannot be triggered remotely to the best of our knowledge. So let's suppose John tries to log into his Gmail account, and once he log in, he receives an email address stating that here is the secret details. Secret details start from AS3F something else. We just copy the URL, the post login URL. We sign out. And in a new tab, we went ahead and just write view-source code and paste that specific post URL. So once when we do that, you just simply search for secret. You will see that the email address was being, the email with the email data and everything is being disclosed back to the source code. So this happens because there was no validation happening again. So what Firefox used to think is, they used to never validate it. They used to simply load it from the cache. So once when we reported this, like all three of us, they quickly went ahead and tried it. But the solution over here was they again did the garbage collection. And once when you try to do view source colon the post URL, it won't display the sensitive information what you have been seeing or performing back during your login period of time. So the example was specific to gmail.com, but it can be the paypal.com, it can be Paytm, or any other sensitive application where it might disclose your credit card information and so on and so forth. So this was one of the very interesting finding which I thought of that would be great idea to having this, because technically, like in most of the organization, like there's a system admin IT guy who never closes his browser. You can, if you are performing any sort of engagement, you can go there and you can see whether all these kinds of vulnerabilities still exist or not. But technically it has been patched, but you can find out in the legacy systems where the systems are not been updated or upgraded, there are chances that you will find out certain set of vulnerabilities or certain class of vulnerabilities still being active. Okay, perfect. Moving on, let's have a look on some low-lying vulnerabilities which was observed during the period of time when I was doing hunting for browsers. So one of the interesting was I swipe right. Now, using the multi-gesture feature in Mac OS, you can actually swipe right to view sensitive information of the application which you have performed. Again, this cannot be triggered remotely. It's a local attack vector. So let me directly jump into the video POC. Yeah, so you have gmail.com and you try to log in. Now, again, still this is still being unpatched because Apple says that there's no security implications over here, but definitely I believe that there's a information disclosure for the application which is being used or was being used by a local user. So once when the user logs in, like suppose in this case, John is the user who logs in, and he receives an XYZ email address, email from stating that this is your current credit card details and so on and so forth. He simply logs out, And once he logs out, using the multi-gesture, you have to just swipe right. And once you do that, you'll be able to find that you can at least go to screenshot back what users have been performing. So over here, when you swipe right, you will be able to see the previous data or the content which was being used by John. So again, I just blogged about it, but having the 90-day disclosure timeline, Apple decided not to go ahead and patch this. But you can use multi-gesture to see previous browsing history or browsing data or the screenshot of past two things or activity which is being performed by the end user. Let's talk about some spoofing-based attacks, because spoofing-based techniques in browser exploitation is one of the easiest way and may have a lot of security implications. So the very first one was DuckDuckGo, which is an address bar spoofing vulnerability. So I created a fake function, like you can name it whatever you want, and I set location to https duckduckgo.com and I use set interval. Now, set interval is a function which tries to load the URL in very slow and very dicey way, whatever time span you have been decided. So here I set fake function to 50. So this is how it looks like. Let me again jump into the POC. Yeah. So you open the DuckDuckGo browser and you navigate to the HTTP server hosting that specific set of code. And once when you do that, you can see it says that https duckduckgo.com, but the content which is being displayed is not actually from duckduckgo.com. So it says that we definitely store your personal information ever, etc. So again, you can play around with this using body.innerHTML code, but the actual magic happens over here using set interval function. And you can define the function to 50, 10, to 5, and so on and so forth. So again, this was being reported as part of the bug bounty program via HackerOne, and they don't have any bounty reward program, but definitely swag and reputation. So this was being patched. The other test case, interesting test case, would be what if domain have emojis? This is a very interesting test case. So on the left-hand side, if you see the lock with https://paypal.com, where you can register a domain with emoji itself. So if you go to ilove.ws, you can register domains with emojis. On the right-hand side, it's like a green check from facebook.com, which doesn't look more authentic, but doesn't look much authentic, but you can have a box.com with a box icon or a paypal.com with unlock. So technically, this only works in Safari because rest of the browsers escape these characters to the puny code. So this might be one of the test cases to perform a spoofing attack where you can buy domains with emojis itself. Moving on, again, this was address bar spoofing in multiple browsers. On the right-hand side of screenshot, you can see the address bar spoofing which was figured out was in Safari, Edge, Opera, the Android web view itself, which is being used by most of the applications out there like Twitter, Telegram, and so on and so forth. Then you have Naver, Whale, Chrome, Brave, Avast, Amazon, Silk, and Falcon from KDE developers. So again, I used before unload function over here. So let me just quickly demonstrate how this thing works. So I have a poc.html. It says that visit this link, https://google.com. Please copy and paste it to the address bar. So when I copy it and just simply go ahead and paste it and hit enter, the URL, the Omnibox or the URL says that it is gmail.com, but the content is, this is alleged, like you can simply play around with this specific content. Now, this was not being technically patched by Safari or Chrome or anywhere else because due to it requires a lot of user interaction. You have to send a crafted HTML page to users, then they will copy that, then they have to paste it. And once when it is being pasted, then the spoofing happens. Due to most of the interaction, user interaction over here, they marked it as informative or low. But again, I went ahead, I created an advisory for this. You can read more about this over here. But again, this was one of the spoofing test case which I found during the research done towards the browser security. Moving forward, let's have a look on web view attacks, what web view attacks are. So what are basically web views? A mini web browser that runs into your mobile application. So if you open Facebook and if you try to click any of the link, it specifically opens that link to an embedded browser which comes with Facebook itself. So it won't open to a Chrome, Firefox, or any of your default browser, but it will try to open it from the inbuilt browser of Facebook itself. So IBM Lotus Note used to have their inbuilt browser. When I say inbuilt browser, like they will have their own rendering engine, they will have their own browser engine, their own UI, or so on and so forth. So the specific piece of code which you see over here is just a simply try and catch statement with an infinite loop over here. It just creates an infinite loop. And once when you visit this, you have to just simply host it. And when you visit this in IBM Lotus Note, the IBM Lotus Note used to get hang and freeze. It won't work entirely. So a patch was pushed from IBM side at a certain stage. When I reported this, I went ahead and created an MSF module for this as well, utilizing the library of MSF remote HTTP server, and 1129CV was being assigned for this. Similarly, there was 1130 when I submitted 2 denial of service vulnerability using the same class of or the same set of code. IBM decided to went ahead and deprecate the inbuilt browser itself from the IBM Lotus Note. So this was one of the test case. So what happened is, if you see this code specifically, when it creates an infinite loop, if you recall from the very first slide where we talk about rendering engine, now this happens because the infinite loop is not being handled by the rendering engine. And once when it is being done that, the browser or the application gets hanged because rendering engine is not capable of rendering this types of infinite loop, and it leads to denial of service. So let's understand the portability of MSF again over here is, you can simply use the HTTP server of MSF, and I simply went ahead and pasted all my code in context of HTML. Then you have on request underscore URL. So again, it will generate a HTTP server, and you have to simply visit it, and the MSF will send the request and capture the response whether the payload was been successfully delivered to the IBM Lotus Note or not. So what all areas are there to explore? Now, this was like we started from what browsers are, what are different types of sectors or blocks has been responsible for. We discussed about what origin is. We discussed about what same origin policy is and how do we evade them. We went ahead and talked about the code execution vulnerability specific to Firefox console, where it allows you to arbitrarily write and read the file state of navigating from different path sectors. We went ahead and had a quick look on the caching vulnerability, the spoofing vulnerability. We discussed about the integer under overflow using one of the fuzzing techniques. But browser itself is a very big component, and there can be multiple areas to explore. So what's the roadmap for the future coming thing which you can discuss or you can have a look on it? You can understand the DOM, the document object model for a browser. Fuzzing browsers DOM basically. Project Zero has a very crisp and clear grid blog about fuzzing DOM. Then you have sandbox escaping techniques. Then you have SOP bypass via source code review rather than triggering it blindly using certain set of code. Participate in browser bug bounty programs. And if you want to read more about disclosed bugs and what you can say from the HackerOne platform, you can simply go ahead and perform site:/hackerone.com/browser. I think they have Brave and similar other browsers in the bug bounty program, so you can read reports of them as well. You can have a sandbox environment to run an open source browser with ASAN enabled. Now, ASAN is address sanitizers. What you can do is you can have a certain set of a sandbox environment or a VM where you are running Firefox or Chrome with ASAN enabled. So what happens is whenever you trigger a crash or whenever there is a memory leak or something else, ASAN will quickly detect it as a runtime. So that can be one of the quick win to understand how things work in browsers. Refer to the bugs which are being published by Chrome, Mozilla, or any other security advisories from the browser vendors. So I think that's it from my side. Thank you very much for having me. I would be available on the Twitter or on the Discord channel. If you have any queries regarding my talk, just feel free to buzz me. So that's all from my side. Thank you very much for having me. So yeah, thank you.